In this lesson, we are going to discuss a statistical machine learning technique called naive Bayes. The goals of this lesson are to learn about a machine learning method that can work with datasets that have very large families of features. This often occurs in datasets derived from text. We also want to understand the theory of Bayes' law and the consequences of naive Bayes classification. To establish the theory, we are going to have to use some math. We are not going to use anything beyond basic algebra. That is, knowing if a number is a product of two others, we can recover the others using ratios, and knowing that the operators of exponentiation and logarithm exchange the operations of addition and multiplication. Data sets with very many features often occur and can cause problems. Two sources of such data sets are data sets that have features that include categorical variables such as zip codes or nicest business classifications. Both of these codes can have tens of thousands of levels. Another way we run into data sets of this nature are data sets derived from free text. These data sets tend to engineer their features on the fly in something like the k-grams or bag of words model, so each row may have very many features selected from an even larger set of possible features. Categorical variables with very many levels can be dealt with automatically. One package that does this is the vtreat package for R. An example of a k-grams or bag of words encoding, as may occur from natural language processing or text classification, is given by looking at this phrase, to be or not to be, that we're going to categorize as being from the author Shakespeare. The derived 2 grams are all the adjacent pairs of words seen in this fragment, to be or not, and so on. The bag of words is a multiset or vector where each of these 2 grams is represented with how many times it occurred in the document. Document being the segment of text for processing. So to be occurs twice and everything else occurred once. Bag of words is not the only way to turn text into usable machine learning features. There's also word2vec, and there are also methods to attempt to reduce the dimensionality of a bag of words other than naive Bayes. Let's establish some background by working an example problem. Our example problem will be identifying or declaring if a document's author was Shakespeare or not based on the 2 grams seen in the document. When working with data sets with very many features, we suggest at least trying naive Bayes. Naive Bayes returns an estimate of class probabilities. It is based on Bayes' law, which is an exact formula for class probabilities. However, naive Bayes itself is only an estimate due to an extra, not strictly correct step, the so-called naive part. Naive Bayes is pretty much the only method we're going to fully derive the theory for. Most methods we strongly advise using a well-vetted, pre-prepared library. Naive Bayes is based on Bayes' law. Bayes' law is the following statement. The probability a document, and by document we mean any segment of text we're interested in, the probability a document was authored by Shakespeare, given evidence, the vertical bar means given, is equal to the probability the evidence would have been seen in a Shakespearean document times the prior probability any given document was written by Shakespeare, divided by a term of the prior probability of seeing such evidence. It is easier to derive Bayes' law from the definition of conditional probability. The conditional probability that a document was authored by Shakespeare given the document evidence is the probability that the document was authored by Shakespeare and it had the evidence divided by the probability of having the evidence. All probabilities here are under possible redraws of documents from some fixed population. The point is that the probability of a document having been authored by Shakespeare and having given evidence is symmetric in its arguments, that we can flip the two things around the and. That means we can apply the law of conditional probabilities twice and expand this joint probability 2 ways, as seen in the slide. The point is, these 4 terms we've expanded to are exactly all the terms in Bayes' law. So we just move the probability of evidence from one side to the other by putting it in the denominator, and we've derived Bayes' law. Let's move on to the naive Bayes technique. The naive Bayes technique is derived by appealing to Bayes' law twice. We say the probability that a document was authored by Shakespeare giving the evidence is what is given by Bayes' law. And we say the complementary event, probability a document was not authored by Shakespeare given the same evidence, is Bayes' law is expanded on the complementary event of not being authored by Shakespeare. We want to estimate the quantity, the probability a document was authored by Shakespeare given the evidence. However, We have 2 equations and 7 unknowns, so we can't expect to solve this. Also, we have not defined what the prior probability of evidence is, and frankly, we have no good way to estimate it. To solve this system of equations, we're going to add more equations to lock down the answer. 2 equations we can add come from the law of total probability, that the conditional odds of a document either being from Shakespeare or not must sum to 1, and the original prior odds of a document either being authored by Shakespeare or not must also sum to 1. Again, the prior odds are the odds that we would have assigned before looking at the evidence. So if we can estimate the remaining quantities from our data, probability evidence given Shakespeare, probability evidence given not Shakespeare, prior probability of Shakespeare, and prior probability of not Shakespeare, then we have enough equations and knowns to solve for the probability a document was written by Shakespeare given the evidence. We ignore the p-evidence term by using algebra to eliminate it as an uninteresting normalization term. That may sound complicated, but the solution is actually simple. We write out Bayes' law twice, replace the unknown probability of evidence with just a normalization constant z, and we know z must be set such that these 2 quantities sum to 1 to obey the law of total probability. What was the point of all that? We need to estimate the 2 quantities, the probability we'd see given evidence from a document written by Shakespeare, and the probability we'd see evidence in a document not written by Shakespeare. Notice these 2 quantities do not sum to 1. The Bayes' law application let us move the evidence from the right side of the conditional probability formula to the left, where we see it now. We can then appeal the law of independent probabilities to say if evidence was conditionally independent, then it would factor, as seen in this slide, that the probability of W words or W observations of evidence given the document is or is not Shakespeare would just factor out to the product. This is the naive step. We're appealing to the theory of independent random variables when we have no reason to believe our variables are independent. In fact, good reason to believe they are not. However, both calculations, the one conditioned on being a document from Shakespeare and conditioned on not being such a document, have the same error. If we're lucky, the error will behave in similar ways in both calculations and mostly cancel out. What do we mean by evidence? For text processing, it's often something as simple as whether a given 2-gram is in a document or not. We would then convert a document into a vector of length w of 2 grams, which has ones where the document has a given 2-gram. Or we could write that as a list or a multiset. When we go to compute probabilities over these evidences, remember all probabilities are just under redraws of documents from a given corpus. These small bits of evidence we're going to call atoms of evidence because they're what we're not going to factor below. Again, we've said the simplest form is whether a 2-gram is present in a document or not. This gives us what is called a Bernoulli model. More involved ways of dealing with evidence could involve counts from the document. That would give us a binomial model. We can also use naive Bayes for other things than text processing. Typically then we build a model for evidence, which is something like a normal or exponential distribution, and then we convert observations into probabilities by either using densities or tail probabilities from these distributions. Let's move on to implementation. The Bernoulli model has the simplest to discuss implementation. Suppose we went through our data set and collected all the following statistics from our training data. N, the number of training examples. N is Shakespeare equals 1, the number of examples in the training set that were attributed to Shakespeare. And then the complementary N is Shakespeare number of zeros, the number of documents not attributed to Shakespeare. NE, for any possible bit of evidence, or any possible 2-grams, how many documents had that 2-gram? NE and Shakespeare is 1, how many documents had both the given 2-gram and were attributed to Shakespeare? And finally, NE and is Shakespeare equals 0, the number of documents that had a given 2-gram in it and were not attributed to Shakespeare. The thing is, all of these quantities are mere aggregations and can be easily computed in a database, meaning that naive Bayes itself can be implemented in a database. From these fundamental quantities, we define the following smoothed probabilities. For instance, LP is Shakespeare equals 1, think of that as log probability estimate, is defined as the log of the number of documents that were attributed to Shakespeare in the training set plus 1 divided by the number of documents in the training set plus 2. This plus 1 plus 2 is smoothing. It's preventing us from forming 0, for instance, if there were no documents in Shakespeare, and it's also preventing the log from blowing up. We define similar quantities for LP is Shakespeare 0, and for every LP evidence given is Shakespeare 1. And again, just by the laws of conditional probability, that's the smoothed number of Shakespeare documents that had the evidence divided by the total number of Shakespeare documents. Given these smoothed probabilities stored, say, in a database table or a lookup table, we can then compute the probability a given document was written by Shakespeare given new evidence. Essentially, the log probability a document is yes or was Shakespeare is the log prior probability the document was given by Shakespeare plus the sum of all these conditional evidence terms we've been saving around. So to compute this sum, we just do a database lookup and sum what happens. We also compute the probability the document was not given by Shakespeare by summing all the same appropriate terms where Shakespeare was 0 in the training set. If log py is greater than log pn, we say is Shakespeare 1. We classify the document into the class. This is enough to build a naive Bayes classifier. If we actually want the probability estimates from the classifier, we need to do a little more. We compute log py and log pn as before. Now, all we in theory need to do is exponentiate both of them to get them out of log notation and divide them by their total or normalizing constant so that the py and pn sum to 1. However, to prevent simultaneous numeric underflow, we do one more trick. The thing is that log py and log pn are both built by criticisms, how unlikely evidence is given documents. Both of them are probably going to be negative numbers of fairly large magnitude. So when we exponentiate them, we're going to form numbers very near 0, perhaps triggering floating point underflow. However, due to the use of the normalization constant z, these are both shift invariant in log space and ratio invariant in normal space. So we pick the largest of them as our shift, subtract it off both. This brings one of them all the way up to 0, and exponential of 0 is 1, so that's not going to be a numeric underflow, and this lets us get a good estimate of the probability. All of this may seem complicated, but this will be clear with an example, and that will be the topic of the next lecture. What you should now know: naive Bayes classifiers can work with datasets that have very large sets of features. Naive Bayes classifiers only return probability estimates due to the naive over-application of the independence principle to factor the evidence. Smoothing is a critical data handling step in naive Bayes classifiers. You must do it, and you can also consider increasing your smoothing constants to make rare data dominate the classification less. Naive Bayes is considered easy to implement, though you don't have to. There are, of course, libraries. In our next lecture, we'll work an example to make this concrete and clear and demonstrate an actual implementation of naive Bayes directly in R. We'll apply that naive Bayes classifier to the plays of Shakespeare and Marlowe to see if such a classifier trained on a couple of those plays can correctly classify additional plays.